Hello, my name is Rob Platt, and this is Robotics, Science, and Systems. So, if all has gone well, you are currently sitting in 130 Hertig Hall, and it is 3:25 on a Friday afternoon. And you are wondering whether you want to take this course, what robotics is all about, etc. So, so I'll talk in some detail about what we're going to cover. But before we do that, I just wanted to start by giving a little bit of an introduction to robotics and why this is something that you might want to study. So, about 10 years ago or so, Bill Gates wrote this article, which it got a lot of attention at the time. So he asks the question whether robotics is the next PC revolution. So in the late 1970s, obviously this was a long time ago, but once upon a time in the late 1970s, computers, that is microcomputers, desktop computers, were not prevalent. And so at that time, computers were used primarily in companies, and they existed as mainframe or mini computers, and they were used primarily as business computers. Sorry, used primarily for business purposes. Now, starting in the late 1970s, there's the invention of something called the microprocessor, which basically enabled computers to be manufactured in a much smaller form factor, and this enabled computers to be placed in the home. Now, before that, there was all this speculation that there won't be a lot of need for computers, for a large proliferation of computers. Really, we just need a small number of computers in the world. But all that changed in the late 1970s with the advent of the microcomputer, because it gave people a chance to play with these things in their houses. And at first, it wasn't clear what the applications would be. At first, microcomputers were a bit of really a hobbyist's toy. But they were cheap enough that people could buy these things and start playing with them, and that's what happened. And microcomputers became, got some proliferation. A lot of people started buying these things. Then software manufacturers started finding applications that people wanted to use on these newly available microcomputers, and led to this snowballing effect, so that by the mid 1980s there are really computers everywhere. So that was really in the history of technology, that was a huge event. And about 10 years ago now, Bill Gates asks a question whether we're approaching a similar point in robotics. So the story is kind of similar. So up until now, robotics has not been really prevalent. There haven't been lots and lots of robots that are used in the house. Typically, you see these things used in more industrial settings, maybe military settings. The question is, are we approaching the point where robotics is going to become consumerized, if you will? And furthermore, if robotics does step into the house, step into these domestic consumer settings, then what sort of applications will we find for them then? So that's really exciting. And of course, from a business perspective, from the perspective of people trying to start companies doing robotics, the question is when? Is it now? So Bill Gates wrote this article 10 years ago, and I would warrant that we really don't have widespread proliferation of robotics yet, but clearly this is going to happen at some point. And a lot of people, there's really I would say a pretty widespread belief at this point that robotics is going to be a really important industry going forward into the future. That is, and I should say, robotics and AI is going to be a huge industry, perhaps the biggest growth industry going into the future. So, right. So let's think about that. So let's think about what I want to talk about where robotics is now from kind of like the commercial industrial perspective and where it might be in the future. So yeah, so the robots of today. So I think obviously, you know, there's already quite a bit of proliferation of robotics out there. So I'm kind of sampling here. So in the upper left here, consumer robots. So yeah, so obviously we have things like the Roomba and a variety of similar type robots, and these these are really exciting. I mean, I have a Roomba in my house, and it's actually super useful because it does a reasonably good job at vacuuming. Obviously, these kinds of robots like the Roomba, are not super sophisticated. Now we're getting to more sophisticated versions of these things. So, for example, there's something called the Dyson Eye, which has I don't know, I think recently become available. It's basically a slightly more sophisticated version of one of these robotic vacuum cleaners. But I guess I think that the big point with these consumer robots is that it demonstrates that it's possible to get widespread deployment of an inexpensive robotic platform. Now, many of these platforms are quite limited, so we haven't really seen quite the explosion that in applications that one would hope for. But I think that it demonstrates that something's possible here. So, all right, so let's think about another big success story for robotics, and that is military drones. So, obviously, I don't know. I mean, I guess this is a little bit removed from everyday experience, but it used to be in the 1990s that military aircraft were piloted by people. No longer, or for the most part, no longer. For the most part, you have these drones. And of course, there's still human pilots, but they're removed from the aircraft. There's, and I guess you would say that the control systems for these military drone aircraft are kind of like on a shared autonomy basis. So the airplane can do some stuff, the pilot does some stuff. There's really been a pretty dramatic shift from piloted aircrafts to these drones. So there's very few human pilots that are trained today. And this is something that people probably didn't foresee coming, 15 years ago. People would have been very surprised about the state of technology today. Now, going to this, what I've labeled here as drones for surveying. I guess what I should say is these are more commercial applications for drones. So clearly, drones are relevant and being used outside of just military applications. So there's lots of commercial applications, domestic applications, so personal applications. So there are applications for surveying a work site. There's applications for surveying the interior of your house. There's applications for drones and just kind of looking around. So you can buy one of these things for relatively little money and pilot the drone and be able to see things from a different vantage point. So, for example, so we recently had Hurricane Harvey in Texas strike the Texas coast, and there are some really cool personal videos created using drones where some guy would fly his or her drone up to some altitude and survey all the flooding that was happening. So that was kind of cool to see. Not the flooding, but the drone. Right. Okay. And then I've labeled this thing here warehousing. So this is perhaps not as evident as many other things might be, but robotics is having a continual impact on making warehousing more efficient. So, probably the big example of this is Amazon's use of something called these Kiva robots. So if you look in this picture, you see that there's these little orange platforms underneath these shelves. And it turns out that those little orange things have wheels on them and they drive around the warehouse. So these shelves are essentially little mobile robots that are driving around, and they can do so in such a way as to make the processing and order fulfillment that happens in warehouses more efficient. Great. So we've talked about we've talked about all the applications that robotics have had today with today's technology, but most people expect that this is the tip of the iceberg. That really there's just a huge future for robotics. So now I want to spend some time and I want to think about what the applications of robotics are going to be like in the future. So obviously the autonomous car is a big one. So I have several friends who are busily engaged in startups that somehow relate to autonomous vehicles. So, and autonomous vehicles has been a dream of AI and robotics for literally decades. I mean, this is, there have been papers since the 80s, folk trying to develop methods that go after some aspect of the autonomous driving problem. And it turns out that in the mid-2000s, there was a series of these things called the DARPA Grand Challenge. These were competitions sponsored by DARPA that really demonstrated that that a lot of the underlying capabilities that were necessary in order to develop an autonomous vehicle had actually arrived. So, and this is something that I'm going to touch on again multiple times over the next several slides. So, for an application like this, like autonomous cars, there's a lot of underlying capabilities that that are needed in order to make that possible. So, for example, in the context of autonomous cars, we're talking about better sensors. We need really sophisticated and inexpensive sensors. We need really capable perception algorithms. Where we need really good planning and control algorithms. All those things have to come together in order for something like this to be possible. You can't be missing any of those pieces. So. One of the first points I want to make is that all of these capabilities, these future capabilities we're looking at is really should be viewed as a combination of underlying technologies that come together to make something like that possible. So, okay, so obviously autonomous vehicles is something that's been people are really excited about, have been really excited about recently. And it's not clear. It's not clear when this is going to happen exactly. So there's a number of technological challenges that remain. There's legal hurdles. So it's not clear, for example, that we can build autonomous cars using today's technology that are going to be safe in snow and hail and in non-ideal conditions. In order for these kind of vehicles to really see the widespread deployment that's necessary in order to make these business cases work, we need to see, these things have to be fail-safe. And it's not clear to me that that we've gotten to that point yet. So there's technological challenges, and if we don't do really well there, then we run into these legal challenges. And more than that, as soon as you start embedding these really sophisticated computer systems in these vehicles, obviously cybersecurity starts to become a big issue, et cetera. So there's a number of different issues here that that need to be ironed out before autonomous vehicles really become a thing. Now, on the flip side of that is the potential that autonomous vehicles hold. So obviously, autonomous vehicles are going to have a major impact on, let's say, taxis, trucking. So, any sort of industry where you pay a human to drive a car or a truck, obviously those can be automated. So it immediately has an impact on those kind of industries. But it could also affect the way people use cars. So today, people buy cars and own them for several years, and once they have that car, it's their car, and they use that car to drive everywhere, to just do whatever sort of traveling they need. Now let's imagine that we have that you live in an urban area, and there is a large fleet of always available vehicles just milling about, and and you've signed up to some account that enables you to just call up one of these cars, and it's basically like Uber, except that it's faster and cheaper and more available. So that's what autonomous cars could make possible. So, and as a result, you could get from the today's model where you own the car to maybe tomorrow's model where you just are using a car as a service on a ride-by-ride basis. So there's really some yeah. So this thing with the autonomous vehicles, I mean, this by itself, this is potentially huge. All right, so let's talk about some other applications. So I've talked about drones already. Companies like Amazon are looking at use of drones for delivering packages. So, again, there's a number of different technologies that potentially are necessary in order to make something like this work. So we need good sensors, we need good perception algorithms, we need good navigation, planning algorithms. So it turns out, so for drones, actually hardware is a huge piece of this. So, and in particular, batteries. So, in order for a vehicle like this to fly, it needs to be able to have this really high energy density battery that's making that's giving it energy, and today's batteries are just not energy dense enough in order to allow vehicles like this to have a long flying time, especially vehicles that require some kind of payload. So that require a significant payload. So yeah, but anyway, so obviously drones are something that for which there's also a lot of potential going forward. Okay, so here's another one: assistance for the elderly. So this is something that that we touch on in my research group. So the idea here is that you have elderly people, you have people with disabilities who would like to live in their homes, but they require some degree of assistance in order to do that. So today, these people make use of some limited degree of nursing services, or people humans who are helping in the home. But obviously, there's just pretty significant limitations to how far you can get with that. Eventually, people who need a significant degree of assistance are forced to move into to leave their own home and to move to an assisted living facility. Now, if we can build robots that can do a better job with some of those in-house chores than they do today, maybe taking on some of the more important roles that these in-house assistants currently perform, then that could change the economics of how long people choose to remain in the house. Because it could mean that even if the robot isn't performing everything that the person needs, it could reduce the amount of human assistance that's required in order to make in-home living possible. So you think about the impending retirement of large numbers of baby boomers in the United States. This is something that could have a pretty serious impact. So, and obviously there's so. Oh, I guess I need to say so. As with the other technologies I mentioned, it's a lot of technologies that have to happen and have to come together in order to make something like this happen. So these these in-house assistants, they need inexpensive but good sensors. They need good perceptual algorithms. They need good planning and control. And now something new, they require some degree of manipulation capabilities because they're going to have to do tasks in the house. All right, let's look at another application. So manufacturing, packaging. So this is something that I guess you can view robots in manufacturing facilities really something that's been going on for several decades now, since the mid-'80s, really. So since the mid-'80s, we've been gradually introducing more and more robots into the workplace. And this is having a very profound impact on the efficiency with which we can produce items. So, it's often said that in the United States, the United States, we don't do manufacturing anymore. There's no, we used to do manufacturing in the 60s, but now it's all service industry. It turns out that that's not technically, that's true in one sense, it's not true in another sense. So it is true that many fewer people are employed in manufacturing. But what's not true is actually the amount of goods produced by American manufacturing today is actually higher than it was in the 60s. So what we've done in the United States, at least, is we've reduced the number of people that are being employed to produce some number of goods, but we've actually increased the number of goods that we're producing. So essentially what that means is that the efficiency with which manufacturing operates has just improved dramatically since the 60s. And a very large chunk of that is the introduction of robotics into manufacturing. So, okay, so how does robotics get used? Obviously in the past, robotics has been used in automobile factories, in like the paint shop and the welding and et cetera. These days there's lots of roles for robotics in roles that in the past have required humans to perform. So, for example, things like there's new roles for robotics in general assembly in manufacturing. There are new roles for robotics in warehouses, so order fulfillment. So Amazon is very focused on improving the efficiency with which orders can be fulfilled. That essentially what that means is the efficiency with which items that you ordered can be placed in a box and shipped off to your house. So the more efficient that process becomes, the more the more profitable a company like Amazon becomes. So there has been and there will continue to be a lot of innovations along these lines. Okay, so here we're back to domestic assistants again. So I talked briefly already about how there was a significant role for robotics in domestic assistance in assisting people with disabilities and the elderly. There's obviously, if you can do those things, there's a huge role for robotics in a variety of other personal or domestic applications. So you're talking about robots that are doing something, performing tasks like the Roomba, but more sophisticated tasks. So instead of just vacuuming, maybe some household robot is going to be able to do your laundry, do a better job with your dishes, to do whatever sort of maintenance tasks around the house are required. And again, there's a variety of different technologies that need to come together in order to make something like this happen. So in order to get these assistants in our houses doing stuff, I mean, for one thing, we need really cheap hardware. I mean, today's robotic arms have come down in price significantly from what they were, but they still cost tens of thousands of dollars. We need to get our robotic arms down to a few $100s in order for these things to really become competitive in the house. And of course, the same thing goes for sensors. Now, in order for these things to work, of course, we're going to need the algorithms, which, side note, that's the focus of this course, algorithms. So perception algorithms, planning, control algorithms, manipulation algorithms, etc. All right. Onward. So one could imagine the same type of technologies helping in other areas as well. So one might imagine marrying some sort of manipulation capability with an autonomous vehicle capability, and you could create maybe autonomous trash or recycling, handling. You could create autonomous package delivery from trucks. There's just a variety of things that could be automated with a combination of these various different things. Okay, all right. So there's all these technologies that maybe will become possible in the future, and of course, the question is when. I think it's very likely it will happen, that all of these things will happen someday. Probably within the next, couple of decades. But of course, various things will happen sooner than later. So starting with the autonomous cars, there's a lot of people betting that autonomous cars are going to become a thing in the not so distant future. So there's a lot of people betting that autonomous cars become reality in 5 years and not 2 decades. So I already mentioned how drones depend on, or at least the kind of the smaller drones that we would be talking about for commercial purposes depend on advances in battery technology. I don't know when that's going to happen. So those applications might be limited because of that. Things like this in-house and the warehouse, the applications in the warehouse, the applications in personal robotics, the applications in assistive robotics, these things, I think these are some of the most exciting applications going forward, because these applications are a little further out than the autonomous driving, probably. And the reason for that is because these applications in the house require some degree of manipulation. So the ability for robots to do stuff with their hands, whether it's doing the laundry or putting dishes in the dishwasher or putting a package on your front porch, there's some degree of manipulation that's required in all of these applications. Obviously that's not required as much for, or really at all, for autonomous driving. So, the manipulation applications might be a little further out, but these applications are really exciting. I mean, first of all, because there's just a huge range of things that might be possible once you start developing really reliable manipulation capabilities. And second, it doesn't have to work all the time. So in order for cars to get deployed for real, they have to be almost 100% reliable. Now, the same is not true for these domestic assistance robots. So in order for a domestic assistance robot to be useful, it needs to be, effective, most of the time. 95% of the time. About 95% of the time, it should be able to load the dishwasher on the first try. If it doesn't do it that other 5% of the time, it's okay, as long as the robot doesn't go dropping the dishes, or it doesn't, catastrophically fail by falling in the bathtub or something. As long as, and there's many fewer legal hurdles. So the way that one envisions domestic robots getting deployed is very different from how cars could get deployed, and that could also affect how these things get out there. So Yeah, so regardless of the exact timeline, it seems clear at this point that these kind of applications, the commercial applications, the robotics industry is going to be growing at a pretty significant clip and an accelerating clip over the next 5 years, over the next decade. All right. Okay, so I talked all about these applications and everything, and that's terrific. So now I just want to spend a little bit of time talking about what you really need to know, which is what you're going to be studying in this course. So basically, we are going to study the underlying capabilities that enable many of the applications that I just talked about. So this is basically those topics that I was listing down the side of the down the left side of the slide in the preceding slides. But I basically see that these are the recurring themes in many new applications. So number one is cheap hardware. If you can't physically build a robot for only a little bit of money, you're not going to be able to have a really widespread deployment, domestic deployment. You still might be able to deploy it in factories, in warehouse situations, but I tend to think that until we get to this widespread deployment to everyday people, analogous to what happened with PCs, until we get to that point, we're not really going to see the kind of taking off, the kind of applications take off that we need to see in order for robotics to really happen. Okay, so perceptual algorithms is so cheap hardware. That's one important thing one thing that we need, capability that we need. Perceptual algorithms, that's another one. So what are we talking about here? We're talking about the ability to build algorithms that could recognize people's faces, recognize cats or dogs or whatever. So, and it turns out that we've actually made huge strides in this area over the last 5 or 10 years. So this is the area of deep learning, where deep learning has really made a huge impact. It used to be that many of these perception problems, many of these computer vision problems were just really, really challenging. And there's just lots and lots of research trying to develop ways to develop better perceptual algorithms. And it's just a really hard problem. And it turns out that these deep learning techniques that you've undoubtedly heard about have had a huge impact, a huge enabling impact, really enabled much better perception than we used to have. Okay, so what other capabilities are we going to depend on going for our future robotics applications? So what I've labeled here is kinematics, planning, and control. The idea there is that your robot needs so your robot needs to perceive, but it also needs to act. So we need some capability to reason about what the robot should do next. And it might be some sort of complex long-term plan. It might be a really low-level controller where the robot responds instantaneously to perceptual information it's received. But regardless, there's this whole area of planning and control that is really important in robotics. Something else that's super important is state estimation. So, this is obviously related to perception. So state estimation is essentially the problem of figuring out what the state of the robot is so that we can control it. So when we're controlling the system, we need to measure the current state of the system in order to decide what to do. And sometimes that state estimation just basically boils down to some perceptual problem, but oftentimes there's some more complexities in there. And there's a long history of various different state estimation techniques, and we're going to, all that stuff is really important. We're gonna try to cover some of the fundamentals there in this class. Okay, and finally, inexpensive sensors. So inexpensive sensors are just like the cheap hardware. You can't do it without decent sensors, and the sensors can't be super expensive. So, so all of these things, my point is, all of these things have to come together in order to deliver the kind of applications that we've talked about already. Now, this course, so this is a computer science course. Our focus is on these pieces of it. So, not going to talk about the hardware, not going to talk about the sensors. Those are really important things, but our focus is going to be on understanding the fundamental algorithm. So I can't cover everything that you need to know in these areas in one course. But what I can do is I can help you understand some of the fundamental algorithms. So I can help you understand 2 or 3 planning algorithms that are fundamental. I can help you understand a fundamental control algorithm. I can help you understand the fundamentals of kinematics, and this will give you a good background, a good basis on which to understand a lot of other stuff. That's basically what I'm after in this course. All right, so let's start talking about the specific topics we're going to cover in list form here. So I'll talk in a little more detail about each of these topics in a minute, but just to summarize here, we're going to cover kinematics, planning, perception, state estimation, and linear optimal control. And as I think I've made this point already, but we're going to, I don't have enough time in the course to cover all details of all of these areas, obviously, but I don't want to kind of gloss over a lot of complex topics either. So what I'm going to do is try to cover 2 or 3 specific important algorithms or ideas in each of these areas in some depth. So cover 2 or 3 ideas in kinematics in some depth, the same for planning, same for perception, and so on. Okay, so right, okay, and I guess the other thing that we want to try to do is introduce you to some contemporary work going on at Northeastern in my lab, but also in some other robotics labs at Northeastern. The idea here is that the stuff on the prior page kind of introduces you to the state of robotics as it up until this point now, and by looking at the research topics that we're currently writing papers about, you can get a sense for what things look like kind of going forward a little bit, and to give you, just try to give you more sense of the direction in which robotics is going. All right, so let's talk in a little bit of detail about some of those topics areas that we're going to cover. So the first one was kinematics. So kinematics is about essentially the geometry of robots. So this is kinematics is one of the first things that people studied in robotics, and this is important because you can't really do much in robotics without first understanding the physical geometry of the robot. So this is kind of the starting point. So a couple of key questions that we want to talk about here. First of all, representing the position and orientation of objects in space. So, for example, you take this this robot here. So this is an image from the DARPA Robotics Challenge, which is, I guess, a couple of years ago now. And there were all these tasks that robots had to perform in order to do well in this competition. And one of them is turning this valve. Now, I want you to think about the problem of turning this valve. In order to, let's say that all you wanted to do was just hard code the exact motions of the robot that it would be required to do in order to turn that valve. Even in order to do that very simple thing, you need to have some kind of representation of the position and orientation of the robot's hand that's going to be required in order to do this thing. So let's say your perception system has detected the location and orientation of this valve, this wheel that it's going to turn, but you can't program the robot to turn that valve until you understand the representation of the how we're going to work with position and orientation of the robot versus the object in three-dimensional Cartesian space. So, yeah, in the plane, position and pose is easy. It's just x, y, theta. But in in the full three-dimensional space, x, y, theta actually becomes a six-dimensional quantity. So we'll discuss that and introduce the mathematical formalisms for thinking about that. The second thing we're going to talk about in kinematics is something called forward kinematics. And this is absolutely fundamental. Basically, what forward kinematics means is it enables you to calculate the position and orientation of the end effector, that is the hand, as a function of the joint angles. So your robot reports to you. It doesn't, in many cases, it doesn't tell you exactly where the hand is. What the robot tells you is what angles all of the arm joints are at, or all the hand joints are at, for example. So what forward kinematics does is it goes from the joint angles to the position orientation of the hand, position orientation of the head, or what have you. Okay? And finally, we're going to look at something called inverse kinematics, which is essentially just the reverse of forward kinematics. So, in inverse kinematics, you're given a desired position and orientation of the hand, and inverse kinematics tells you what joint angles you need to go to in order to get there. So obviously, inverse kinematics is a pretty important thing. It's hard to think about how we're going to program our robot to put its hand on this valve if we don't have some mechanism for calculating what joint angles the robot would have to be at in order to get there. Because remember, many of these robots, we don't program them in terms of the positions of the hand, we program them in terms of what joint angles to move things to. Okay? So all of that is the subject of kinematics, and that's where we're going to start. Okay, then we're going to move on to planning and control. So, so this is, I guess I would say it's probably the most important topic in robotics. Perception is right up there, in my opinion at least. Perception is right up there with it, but planning and control is that's really fundamental. So, so the problem that we're trying to solve here is we want to plan or otherwise create a controller for moving the robot in order to perform some task. So in the simple, maybe the simplest case is to think about this, what's going on here on the left. So let's say that our robot has detected, using its perceptual systems, the position and orientation of one of these objects, which is lying here on the kitchen counter, and we want to pick it up. We want to grasp the object. Okay, so I just got finished telling you that that we needed to solve some inverse kinematics problems in order to do that. That's true. But we also did that, but that's not sufficient. We need to we need to do even more. And the problem is that if we just blindly move toward a satisfying set of joint angles that gets the hand there, there's no guarantee that that the robot's not going to collide with a bunch of objects on the way over there. So in this drawing here, as you can see, there's all these other objects that the robot has the potential to crash into, and it's, obviously we want to be able to move the robot's hand to some grasp configuration without crashing into the counter and without knocking things over. So that I would say is one of the simplest instances of planning conceptually. Although that just doing that problem is actually a relatively challenging problem, and we're gonna think about that. That's one of the first things we're gonna think about. And actually, in the history of robotics, some of the most important advances were made in planning in response to this exact problem here. So we're going to talk about that. So planning and control are actually linked in a pretty intimate way. So an example of a control problem is this problem here in the upper right. So what's going on here is that the robot is obviously walking over these cinder blocks. Now this is a challenging control problem because keeping a robot like this standing up is no easy feat. So there's a number of things that have to happen. The robot the center of gravity has to remain within the footprint of the robot, at least in the statically stable case. The robot has to make forward progress. The robot has to be able to reason about what flat surfaces or what surfaces it wants to step on, and it needs to be able to do all of this within some relatively tight control loop. And that means that it needs to be able to do all of this at, let's say, 10 hertz, 100 hertz, like 100 times a second. It needs to be able to update the control signals going to those legs. And that's something that can be very challenging. Now, walking, control is a subject that's been studied for a long time in engineering, and often, at least early on, the control was studied in the context of something called linear control. Now, linear control is not enough. It is not, linear models are just they're too simple to cover a lot of the instances that we're interested in robotics. So in this course, I am going to introduce you to some linear optimal control concepts, but we're also going to think about nonlinear control and how we can use planning inside the control loop in order to begin to solve problems like this. And I guess I'll just mention quickly, in the lower right-hand corner here, this airplane doesn't look like a robot, but there's, the problem of, as it's called, nonlinear control is actually pretty far-reaching. So this is, these control techniques that are studied in the context of robotics have applications far beyond robotics. All right. Okay, another topic that we're going to study is state estimation. So again, this is a topic that's been studied in engineering for a long time. It's something that is really critical in robotics, and I'm kind of lumping a lot of different ideas under the title of state estimation. I mean, probably that. So I don't know. Fundamentally, what we're going to study here are things like particle filters, Kalman filters, methods of estimating robot state based on noisy sensor information. So I guess I should back up and say the problem that we're trying to solve with state estimation is to turn our noisy robot sensors, that is, let's say, laser sensor output, sonar sensor output, camera sensor output. We have all this sensor output, but in order to use that in the context of planning or control, we need to make sense of that somehow and turn it into reliable estimates of the quantities that we need in order to in order to make our robot do our thing. So and that's exactly the problem that is solved, or at least addressed, by methods like particle filtering and Kalman filtering. Now, in general, the problem is very challenging. So, in response, what you find are some of these more, particle filter, Kalman filter, are some of the more popular techniques for approaching the problem. Now, I'm also going to talk about, under the context of state estimation, some perceptual problems. So the problem of so one of the things that's probably been a huge win for robotics in the last 15 years is something called SLAM, simultaneous localization and mapping. And basically what SLAM does is you have some depth sensor on your robot, like a Microsoft Kinect or some other type of gaming sensor, and the sensor gives you this depth information. And what SLAM does is it integrates all of this information into one coherent three-dimensional map of the environment in which the robot is moving. And furthermore, given this map, SLAM is able to localize the position and orientation of the robot in that space. Now, obviously, if your problem is robot navigation, robot motion, then this is absolutely fundamental, to have a reliable geometric sense of the environment in which the robot is moving. Okay. So we're also going to talk about perception. So this is this is something that I would say is on the boundary of computer vision and machine learning and robotics. So clearly perception, especially visual perception, that's basically a field by itself, known as computer vision. So there's really there's a lot to talk about, and typically perception draws very heavily on machine learning, and to the point where these fields are almost indistinguishable now. So anyway, we're going to, obviously, perception, it's this field, but it's also incredibly important to robotics. So we're going to talk about a couple of perception algorithms that are particularly relevant to robotics. So specifically, I'm going to talk about a couple of really fundamental kind of old school algorithms. One of them is called RANSAC, another one's called ICP. So both of these methods are, that's what's being shown in some vague sense in this picture here. So suppose that you have a depth sensor, Microsoft Kinect, say, and it's looking at the environment, and you want to estimate the position and orientation of some object in the environment that you want your robot to pick up. How in the world could you possibly solve that problem? Well, it turns out that both RANSAC and ICP are candidates that you could use to localize a pose of an object in a point cloud. So these are some old school algorithms, but yeah, these are just continuously used up until today. So these are really important things to know. The other thing we're going to talk about is some more current perceptual algorithms based on deep learning. So deep learning has had an enormous impact on computer vision, to the point where deep learning has basically taken over. It's difficult to get papers published in computer vision if you're not doing deep learning, which is probably a bit of an overreaction. But the point is that deep learning is just a huge topic in computer vision. And so deep learning has enabled, essentially, first of all, I'll say deep learning is essentially neural networks. All we're doing, and neural networks is an idea that's been around for several decades, and it turns out that the field discovered some new applications for special neural network structures a few years ago, and in the early 2010s, the field discovered some deep architectures, deep neural network architectures that enabled us to really do new things with computer vision. And in particular, deep learning enabled us to do much better job doing things like object detection. So it used to be that you point the camera at some scene and you try to detect like where, let's say, the oranges in this picture are, and there were just no good algorithms for doing that. And the reason it's so challenging is that there's so much variation between individual instances of oranges and individual instances that belong to the class of bananas, that it's just really difficult to build an automated detector for locating those things in images. Now, it turns out that deep neural networks can be used to solve that problem very effectively. So in this course, I'm going to give you a one lecture, maybe 1.5 lecture introduction to some of those ideas. Deep learning has not yet had a huge impact on robotics, but this is probably something that's coming down the pike. Okay, so I guess that summarizes the major things that we're going to cover in the course. So anyhow, so just in terms of the mechanics here, so the things that you need to bring to the table in order to take this course, in addition to being interested in robotics, you need to have an ability to do some basic programming in MATLAB and Python. So specifically, I'm going to give, I think I have, it'll be on the next slide. I have 4, maybe 5 programming assignments that are all in MATLAB. And the reason we're doing it in MATLAB is that I want to place the focus on the algorithms and not so much on the mechanics of interacting with these robotic systems. So so you need to be able to program in MATLAB in order to do those assignments. And then there's going to be a final assignment, this end of semester thing, which you can do in MATLAB if you want, but my preference is for you to do it in Python because I want you to be able to interact with this this simulator, which is relatively realistic and that we actually use in the research lab. And the other prerequisite is for you to be able to be somewhat comfortable with linear algebra and math. So I haven't said it explicitly so far, but this course is an algorithmic introduction to robotics. So we're not actually doing any, you don't have to do any hardware development in this course. If you want to involve robotic hardware in your final project, you're of course more than welcome to do that. But I'm not providing hardware as part of the course. So the focus here is on understanding the algorithms that would enable you to do stuff with the hardware. And because of that focus, all of the work, or just about all of the work, is going to be in simulation. And I guess this is a little far afield, but in order to understand a lot of these algorithms, you need to be to be at least willing to understand some somewhat sophisticated topics in linear algebra. So I'll give you an introduction to these topics as appropriate, but if you're not already familiar with linear algebra, you have to be at least willing to learn things on the fly. All right, the book. So we're going to, for various different topics in this course, I'm going to draw from different source material, because unfortunately this is one of the things about robotics is that there really is no one definitive piece of source material. But this book right here is, I like this one in part because the MATLAB assignments which we're using in this course are built on top of a library which is developed by the author of this book. So the author of this book is this guy called Peter Cork, and the software which this book makes reference to and has assignments for, we're building on top of that software as well. And furthermore, this book covers a good chunk of the material that we're going to cover in this course, topics in kinematics and planning. Now, there's a lot of other stuff that's not covered in this book, and the material that's not covered in this book will be made available via free downloads of books or other kinds of source material, which is linked to the course website. Okay, yeah, I mentioned that there were 4 MATLAB assignments. So in this course, I reserve the right to introduce one more MATLAB assignment if the mood strikes me. Basically what I'm after here is, I've already said that I want you to be familiar with key topics in robotics, and these MATLAB assignments are basically going to force you to implement some of those key topics. And that's, what I want you to get out of this course is a working knowledge of these robotic algorithms. And I think that the only way to do that is for you to actually implement at least simple versions of these algorithms yourself. So that's what you're going to do in MATLAB. Now, at the end of the course, okay, so in order to do those MATLAB assignments, you're going to need to have access to MATLAB somehow. If you've never done MATLAB, that's fine. Again, you just have to be willing to do it, get it installed, learn how to use it. MATLAB, as a programming language, is pretty straightforward. MATLAB it's not a challenging language to learn, but if you don't know it, then you're going to have to be willing to spend some time to do that. If you don't have any programming background at all, I think that might be an issue. Okay, and then the final project is going to be this directed project that's going to involve interfacing with OpenRave. So OpenRave is a robotic simulator that we basically use in research in our lab. So creating a project with OpenRave is about the closest that I can come to having you do things with real robots without actually having you do things with real robots. So the OpenRave robot is essentially the same as the real robot, but it's in simulation. And these days, everything gets done in simulation before it gets tried out on the real robot. So this is I think that this is an appropriate focus for your final project. So anyhow, right, so we use OpenRave in just about everything we do in my lab. So this is very current in terms of research. So anyhow, right, so there's going to be one final project in this course. I call it a directed project because I am going to make suggestions. I have a list of topics that you can choose from. Now, if you don't want to do a project on any of the suggested topics, you're more than free to propose a topic yourself and then do that project. So it can work either way. But my preference is that the project involves doing something in OpenRave. Okay, so in order to use OpenRave, again, there's a little bit, there's potentially some challenges with the software here. So I did this last year and it didn't present too much of a problem. Basically, in order to use OpenRave, you need some version of Python 2.7 installed. I don't think that I think you need to have Python 2.7 or something thereabouts. You can't. I don't think it's going to work with like the latest version of Python. You want ideally you're going to be using Ubuntu 14.04 or later. But I believe that you can get this system working on a Mac or Windows platforms as well. But there can be additional systems challenges in doing that. Okay, so in doing the final project, there's a potential for you to need to spend some time getting OpenRave and Python installed on your system. All right.